We'll also discuss what is morphometry. Quantitative measurements and mathematical analysis of Earth's surface forms. So as you can see that there are different drainages like dendritic, radial, talus, rectangular, and irregular. So we need some kind of a measurement in order to understand how these drainage patterns are affected and how it is uh, are they, I mean, just controlled by structural, or is there any tonic control? So, what is morphometry? Morphometry provides an objective framework to describe landforms, geometry using measurable parameters like length, area, slope, relief, and network topology. Unlike qualitative description, morphometry relies on numerical indices enabling scientifically reproducible comparisons across basins, regions, and tectonic settings. The morphology of a basin is a cumulative product of climate driven erosion, fluvial incision, weathering, tectonic uplift, and lithological resistance over time. Morphometric indices encode valuable information about landscape evolution, hydrological behavior, and tectonic activity. So, applications across earth sciences, tectonic geomorphology, mountain front sinuosity, right? We will discuss that in detail. And then valley flow ratios, stream gradient indices, and asymmetry factor in for neotectonic deformation and active faulting. Okay. And in engineering geology aids suitable assessment for dams, reservoirs, and infrastructure projects through terrain analysis. So it's very important that we do these kind of analysis. For example, if we are building a dam, right? So whether there is a active fault in that area close to the dam, if there is a active fault and the reoccurrence interval of that active fault is around, let's say, 50 years. So within 50 years, this there will be an earthquake in that area. So if we are not taking care of that fault, then that dam can be destroyed by that activity. So it is very important when we are doing these engineering uh, assessments that we understand or we explore that area through remote sensing, through field work, and through literature also to understand if there is any active fault. In hydrogeology and watershed management, guides flood modeling, runoff estimation, soil erosion studies, watershed prioritization for resource management. Environmental and climate studies, basin shape, relief influence, sediment flux, peak discharge patterns, and landscape sensitivity to change. So, morphometry translates the form of landscape into quantifiable matrices that reveal its function, history, and dynamics. By measuring Earth's surface geometry, morphometry provides a powerful lens to understand the processes that have shaped and continue to shape our planet's dynamic landscape. So, for example, I can just show you some examples or some questions. So, if we see the drainages which are formed around Chandigarh, we can see some drainages which are formed on Chandigarh antique line. Even though these rocks are shivalik rocks, we can try to identify. Uh, पूछना जरा उनसे कैसे ये गूगल अर्थ कैसे आएगा इस पे। My screen is not projected here. I want to show this screen on there. नहीं आ रहा है ओनली पीपीटी पीपीटी से मिनिमाइज करूं क्या नहीं नहीं अच्छा मैं एक बार इसको मिनिमाइज करूं प्रेजेंटेशन को क्या पता उससे आ जाए हम्म किस चीज के हैं हम्म, मैं तो भी लेक्चर ले रहा हूँ यार हाँ हाँ दिखाना किस मेरे ने किसने भेजा आपको now if we just see some of these drainages for example in this area if we zoom so you are looking at this drainage now you know this one you see this drainage so the question we can ask why it is like this why the shape of this drainage is like this what is controlling that because these drainages they are formed like and we can again see the drainages which are formed on top of which are formed on top of the Chandigarh anticline and there are paper written where people have shown that there are some deflections of the drainages and because of that they are trying to identify or mark some active faults in this area. So sometimes these drainages and the water pattern flow can also influence how these drainages are built. Okay. So we need some kind of a function, some kind of a tool in which we can quantify these values. Stream order, understanding drainage network hierarchy. Stream order is a hierarchical method of classifying drainage network components according to their relative position and branching complexity. The most widely accepted system is Taller's stream order, which assigns numerical orders to stream segments based on tributary arrangement. Stream order is a fundamental parameter in morphometric analysis because it provides a structural way to quantify the drainage network's organization, branching pattern, hydrological behavior. This classification system forms the fundamental for understanding how water moves through the landscape. So the first order streams, the smallest channel with no tributary, usually originating in a waterhead region. So that will form the first order stream. Second order stream, when two first order streams join the channel downstream, becomes a second order stream. Third order progression, when two streams of the same order merge the downstream segment, takes the next higher order, that is the third order. And then following, when a lower stream joins a higher order stream, the order remains unchanged. Okay. So this process continues throughout the basin until the main trunk stream reaches the higher order, creating a complete hierarchical network. So as I was showing you in the morning, if there is a drainage basin and there is a fault, we have seen that thing in a Hitproli region. That we have if some active fault is there and if it is seeing the uh, main channel, the trunk channel, then the erosion is in the because here in Shivaliks we have soft rocks, right? So erosion progressively you can see that it is going slowly and slowly upward. It is causing a headward erosion. So in a way, what we can see is that so for example, like in what we saw in Cape Raleigh, so these are the mountains, let's say, and there is some river, some tributaries are coming like this, and uh, you know, let's say there is some kind of a fault or something. And because of that, some displacement is there. So the erosion, because in this area the rocks are very soft. Uh, Upper Shivalik rocks, they don't have any cementing material. So what is happening if the river is going like this and somehow there is some change in this, then what will happen because of this erosion? Now the erosion will start happening like this, right? This stream, when there will be change in gradient here, now the erosion will start happening. Now this stream is able to see that yes, there is some change in this basin. And now the erosion will start to happen in this area. So similarly, this outward erosion will start propagating upward into the drainage basin. And we are able to see that very clearly in the field that now one thing is there because this stream is getting lot of water and there is less stream power in the smaller stream. So the amount of erosion will be more in this one as compared to this one because here you have more stream power, so you are able to erode more in the main main channel. But in tributaries or in the small, uh, you have lesser erosion. And we have also seen that when this erosional front will progress towards the uh, higher reaches, it will then cause some kind of a small landsliding event here. Now this whole basin now starting to erode, and it will go to a the if the starting the basin was like this elevation wise, this is basically elevation, let's say, with length. So slowly it will, because of erosion, the river wants to bring it to a kind of a base level. And our idea is to uh, the water is falling, the rain is happening in the drainage basin. Our idea is to quantify with some numbers whether this is tectonically driven or it is just simple erosion is happening. Okay. And there are many basins. Let's say there is a fault. Let's say there is there is a drainage basin, and if one fault comes along this, and it let's say it displaces something like this. So what will happen? This basin will become little bit like it will be displaced. So it will be something you will see that this corner is here and it is displaced along this fault movement. You know. So if a strike-slip fault, let's say there is a fault and it is cutting through the basin, because these basins they are formed due to long-term erosion, right? Long-term erosion is happening and water is falling. Now there are other factors which are controlling the how this drainage network will form. Other factors are like the strength of the rocks. If the rocks are very strong, for example, let's say you have a strong sandstone or other metamorphic rocks, then the erosion will strongly will depend upon the strength of the rocks. But especially in upper Shivalik rocks, where we have these mountain, these anticlines, there it is more or less topography driven, and you can have some kind of anomalies. And in Himalaya, we see these kind of truncation of some basins, drainage basins, because of active faults. So if a fault is crossing a basin, so you can think in your mind that the basin was forming like this, but now it has displaced. And especially where you have stronger rocks, there you can preserve this kind of a anomaly for longer time scale. But if the rocks are weak, then this will again merge with this, and then maybe we will not see that displacement. Okay. So one thing is that, and there are other things, that basin can be tilted. The river might shift this side or that side. So those kind of things can also happen in the basin. And if you see basins in Manikaran region, if in Manikaran, if you see basins, you can see that those basins are very heavily, the rocks are very strong, and you can even see that in those cases you can have a leaf-like pattern. The basin is something like this. The drainage network in the Manikaran area. So now in this case, if we see a basin like this, what is controlling that? Why it is forming very clearly like this? So you know I can just show it on this. So now I will show you some other example in which you see a basin, and you will just see this same thing. It's okay. You see this? You see this part? Now we are looking. This is basically Marine right? And if you see this basin, this one, you see it's like a leaf, right? So the other thing, even though there is long-term evolution of these basins, so I think that this is controlled by joints, and in the rock mass you have different sets of joints. So depending upon which joint is more resistant, you know, so weathering will happen according to that. So you can see that this is a beautiful basin with this kind of a pattern. So the point is, yes, the rocks are hard here, no doubt, compared to Shivaliks, but you can see clearly a very good shape. The other thing which we can see in terms of geomorphology here in this area, you know we can see a lot of villages, and for example, like, let's say this basin, you know this one. So do you think it is just simple erosion has formed this basin, or there are some other processes like geomorphic drivers which can make a basin like this? Yes, any guesses? In the morning we discussed what are various geomorphic drivers which can change. Okay, so you can see now. I think this is Vyas River. Vyas River is flowing in this area. So you can see that there are some villages here. This village is here. So in hilly terrains, villages are generally where you have some kind of a soil cover, right? So from where this soil is coming? Glacier, right? Yes, we discussed in the morning that there are three main drivers. So basically, right now you are not seeing the glacier, but in the old times when glaciation was there, these areas might be covered by glaciers, and glacier do lot of grinding, and that grinding basically produces these shapes, and then you will have soil on, on the higher reaches of the mountain. So the now the point is that some of the maybe some of these drainage basins, not today but previously, they were carved by the glaciers, by the movement of glaciers. Now we are maybe not seeing them, right? So if you see the topography of Himachal, right, you will see a lot of areas. Like you can see that okay, there was a glacier. There are other factors also, no doubt about it. Now if we see this valley, this one, so you can think of okay, this valley was coming, and you will be able to see you if I just zoom in this area. Let's see, you know you can think of that okay, when glacier was coming, it was coming, and you can see some kind of a blockage here. You see this, this now this is a kind of a anomaly in a drainage basin. So if I'm looking it like this, now my mind will start thinking okay, maybe some fault is doing this, because if this is a drainage, it should have, this side will be, should have been on that side, right? It is just blocking the way. You see, if this rock is like this, and then, you know so if you just search in, you will find many areas where, you will have U-shaped valleys which are not connecting with the river. You have U-shaped hanging valleys from where the glacier just falls down. So the idea is, even though today we are not looking at glaciers which are covering all over the Himalaya, but previous, if we go 1 million year back, glacial, interglacial periods, then this area was covered by glaciers. As we can see today, these, you can see these areas. You have lot of this, and you can see how it is formed. So if we are thinking in a longer term scale, you know, uh, then wherever you have rivers, maybe at previous times the glaciers were flowing there, and you will find a lot of sediments in Himalaya where you have fluvio-glacial. Fluvio-glacial means they are derived from glacier also and from river flow also. In the rivers, the pebble will be more rounded; in glaciers will be more angular, unsorted. In river, you have sorting of uh, sediments, right? So, so now you can see this is the Byas, right? Byas is starting from somewhere here. So this whole valley, this Kulu Valley, So previous time maybe the glacier was flowing here, but when they retreated, now this became a river, a perennial river. And same is the problem of Joshimath. In Joshimath also now there is a concept of north and south slope also. You know, the slopes which are facing the sun. You know, so these slopes the ice will melt, but the other side you will have vegetation, trees, and everything, right? And you will have more or more soil formation on the southern slope. So the population will always sit on these slopes. For example, Rekong Pio is also, a area where you have subsidence going on. But the point is from where this soil came. It was not of a fluvial origin. It was a origin of a glacier, because glaciers have grinded and produced that soil. Now we have made houses there, and now those areas are sinking. So sometimes these landslides are caused by some kind of, geomorphological. These are due to some geomorphological features which on which we are building houses. So same thing is happening in Joshimath. Joshimath also, where we have this subsidence going on, all that soil, you can even see a shoot of glacier coming down, and that area is now sinking. And this is a big problem in Himalayas, because with the rainfall, every year we are losing a lot of soil. And a population can sustain on top of a soil. If you have rock, you cannot do anything. So this is a big challenge for these Himalayan states. So now we have this concept, right? Now we understand that okay, these rocks, they might have seen lot of glacial and interglacial periods, right? Because these are very old rocks. But yes, you can see signatures of different rocks on top of this. So now if let's say we see a active fault which is cross cutting this. Now you see this, in this we are seeing a lot of these linear features, but they might be bedding of which is just cut by the erosion, and it looks like a small linear pattern. Okay, so if we want to find a fault, so I can just show you here one example of a fault. So now you see this drainage. This side you have a drainage divide, but on this side you have a drainage divide and again drainage divide. So this in between, what is happening? So actually there is a strike-slip fault which is moving in this zone, and it is making a backhill facing scarp. Let's say the mountain is like this, and there is a fault which is a thrust, so it can do something like this, and so it will look like this because the fault maybe has moved this side up, this side down. Let's say now this is known as backhill facing scarp. Backhill. This fault scarp is facing backhill. you know so we see some kind of a feature like this in a mountain. That means a fault maybe is passing through that. And we see a lot of areas, especially where this kind of backhill facing scarp is formed in the terrain. Now what happens is the fault is formed. Let's say we don't have any datable material. So what people have done is, like, you will have rainfall, some erosion, slowly a sag pond will form here, and then you will have sedimentation. So now in this sag pond, you will have layers of sediments. So we can do drilling, take out these samples, and these can be dated. So when we date that, we know the age of the formation of this sag pond. Approximately, then we can put some constraints when this fault was active. Because in the sand, in the soil, we will find quartz, and quartz we can put in a machine and we can calculate its age. Okay, so yes, so this is again, you can see this active fault is passing through. Now this is Renuka Lake in Himachal. You can see this is Renuka Lake, uh, and this Giri River used to flow from this side like this. And there was some tectonic event. Because of that, now this river has shifted to this side. But previously, it used to flow from this direction like this. So a tectonic event can uplift an area and change the course of the river also. So what are the geomorphic markers? We see this very steep scarp here also, and there are some traces, linear traces of this old displacement, which are still you can follow across many ranges. You can see some kind of a displacement features which are present in this area. So the point is there are many factors which are shaping these older drainage basins. Their lithology is controlling Some of the drainage basins have seen lot of glacier interglacial periods. Maybe they have seen some earthquakes also. And maybe a fault is passing through them. So all these factors might have contributed in the formation of these drainage basins. Somewhere some factor is more, somewhere some factor is less. Okay. Now, if you look here, there is a valley on top of a mountain. There is a valley which is formed on top of a mountain. So you can ask, what was the origin of this? I also don't know, but these are kind of things. This valley is formed on top of a mountain. On top of a mountain, you have a valley. What is controlling that? Whether it's a fault, maybe paleo fault or something. So there are so many anomalies which you which are there in the field, and we can try to understand them. And sometimes when you have landslides, you know, uh, because of that landslide, if let's say there is a big this basin is there, some landslide happens. Sometimes rock avalanches, in a rock avalanche, what will happen? All the rock maybe fall and it will make a deposit, you know, some kind of a deposit in front of this. So this is maybe a rock avalanche, so it will have a lot of uh, material which is just in front of this. And sometimes this can cause damming, damming, and it can break suddenly and cause lot of disaster. And we saw these basically in Kyrgyzstan. Lot of these damming, basically damming by paleo earthquakes. So paleo earthquake caused lot of damming, and lot of these rock avalanches are in front of the in the drainage basin. And somehow if the lot of rainfall or something happens, they are triggered and they can break any dam or things like that. And there are features in Himalayas also, which are present like this. There are a lot of places where you will see rock avalanches. Rock avalanche is basically, it's a kind of a paleo landslide which all the material is just lying nearby in drainage basin, and it has not been remobilized, because the size of these rock avalanches can be very dangerous. If there is a dam downstream, lot of debris and rock comes, it can destroy that. So we need to also understand or map these kind of rock avalanches or these kind of debris material, which sometimes the problem is that sometimes we think that these are just glacial born moraines, because it is, sometimes tough, because moraines, yes, moraines are the product of glacial movement, no problem. But sometimes if we have paleo earthquakes, they can also make these rock avalanches, right? So, and we have found some rock avalanches in Uttarakhand. We, we have found those sites, and we are working on those sites, that if they can get mobilized, they can cause a lot of damage downstream. You know, so now you are understanding that okay, a drainage basin forms slowly and slowly with time. You know, it will have some kind of parameters, but if that drainage basin is deflected or changed, some anomaly happens, then our eye setting should be like that, that yes, we should be able to recognize, okay, there is something is happening, this fault is passing, let's say 5, 10, or 20 kilometers. Because if you have a drainage or a drainage divide, you have rainfall, so this drainage divide will slowly degrade. you know if something is happening in this or this basin, yes, we are thinking, okay, some tectonics is going on, maybe it is not just pure erosion, right? because we are because erosion will always happen, no problem. Erosion will always, whenever you have rain, you have some kind of erosion is going on. But tectonic is just instantaneously, a tectonic driver, which is changing the shape of our basin. Okay. So when I see any area, I try to figure out how this has formed. What is the anomalous thing here? Is it normal or is it behaving abnormal? So all these things you have to keep in your mind, because when we are just today, I'm going in the field, I'm looking at a surface or a mountain, I'm thinking, oh, glacier is not there or something, but it has all those effects incorporated into the terrain. So let me show you one more example where you can clearly see a fault. This is of course a paleo fault. Yes. So now, yeah, this yes. Okay. Now you, all of you, try to observe. Do you see any anomalous thing in this figure? Anybody? Sarabjit? Center of the river. Here, there is something. This, yes. Okay. Anita, Sumit, anything? Uh, you can take your time. Little bit time you can take. Try to see something anomalous in this. Arnav, are you able to? Can you identify something anomalous in this figure? Okay. Maybe something going north-south or something going east-west. East-west? Where? Where? Or this one? North-south also? Where? You can show me? Yeah. Which one? You can point it out. Yeah. Okay. Yeah. So now, yes, Anita, yes, she is right in telling that there is something, there is something going, and this is a trace of. Okay. So let me show you very interesting feature here. So this is the paleo fracture, or you can say fault plane. Whether it's active or not, we cannot comment on that right now. But yes, there is a Sirmaur Degree College. Is right here. There is a college which is built on top of fault plane. Because what happens in mountainous areas, you have a slope like this, right? Wherever you have some kind of this, so you get some kind of space. So the college is built on top of that. I think it's buffering. The picture will become more clear. Is it clear now? Okay. So now you see this fault plane. You can clearly see this fault plane. and right here is the college. So these kind, and now the important thing is that this fault is, this fault fracture is continuous approximately 50, 60 kilometers. It is not just at one place. It is cutting across all the mountains. And I will say, you can see that, you can see you are able to see the fault trace, So somewhere here it is going like this. And we will also show you in the practical session, we will show you some cartoset images in a which anaglyph, you can see an anaglyph. And then you can have a depth perception how a fault can be seen in 3D. It's like, aerial photography where you are just flying from top and you're looking down. So now one more thing I will say about this. What do you think? This drainage basin is okay? This has evolved right or something anomalous for this drainage basin? The sea like that. Anything anomalous? We can see, yes, there is a fault in its, oh, kind of. This basin, let's say observe this basin. To me, it's little bit anomalous. And why it is anomalous? Because this side is okay, we are eroding. Now, this side also we are eroding, but this mass has somehow come up into the drainage basin. So I will say that this is anomalous because if it is, you know, both sides should have been similar, but this side is coming. You can see that it is coming into the basin, and the fault is also. We can see the fault trace also, right? This drainage basin, is there any anomalous thing in this drainage basin? Do you see anything anomalous basin which is right above this one? So now if we think in terms of, okay, erosion is happening and it is merging into this, I will say something is passing here. Why? Because right here there is a triangular facet. There is some new small basin is coming up and it is kind of blocked. It is kind of little bit blocked by this rock. So now my mind thinks that, okay, there is some kind of a lineament is passing through this basin. Maybe I need to go in the field and check whether it's a fault. And then I can mark the orientation of this. And maybe I can see other hills also that whether it is passing or not. And if somewhere near a river, maybe this fault is truncating a quaternary sediment, then I can even date it and put some constraints. Okay, this fault moved that time. So we can put some age constraints on top of this fault. Because if this mass was not here, imagine like that, then this basin would have continued easily. But this is coming into this, and this one is also coming into this. So these two, maybe something is passing. One strand may be passing like this, and merging into the one fault plane. Okay. And some of the basins, yes, they are maybe sometimes they are more or less erosional, purely erosional. Now we can see this area also. There are drainages which are coming like this. So if these drainages are just going into the river, it's fine. But if somehow this drainage is falling, making a waterfall and then going into the river, it means there was some kind of a uplift or something which happened. So just by looking at drainages, when we are going in the field, we can get an idea, okay, this area is stable or it's, some tectonic activity has happened. Because if some drainage is coming, it will make its path up to the river. But if it's just falling like a waterfall, and lot of waterfalls are falling, it means this rock has gone up. That's why it is falling, and slowly it will make its path, but it will take time depending upon the strength of the rock. So when we are going in Himalayas, we should always be thinking about all these things. And there is another thing. Now there is very interesting thing is happening here. You see that now this basin is totally okay, done. This one has lot of these erosional headward erosion is happening. So you can think of as a landslide or some debris material is coming. Now there is a basin in top of it, which is kind of hanging here. You know, and no doubt that when we are talking about erosions, that is mainly controlled by uh, the strength of the rocks. For example, if we see in Dehradun, right here, there is this big landslide, and there is Stonegad thrust is passing through this area. There is a fault, paleo fault is passing right here. Stonegad thrust like that, and you have a big landslide on top of it, right? Now the idea is if this fault, now you can see this fault is again, you see this drainage basin, this fault is going like this, this fault scarp is going like this. In this drainage basin, the more or less erosion is happening here. But in the adjacent valley, the whole rock mass came down. So these are very interesting questions. Why it is happening like that? What is controlling it? So you see, in this one, there is a big landslide. In this one, only a small portion of this basin is having headward erosion. This one whole is going down. This one only here. And there are many anomalies, like that. One more thing I want to show you now. Yeah, there is one more geomorphic feature which is present on top of a mountain. It will look like a hanging this thing, but it is not. So if we go into, yeah, when I first started working, this is basically Renuka Lake. I marked it as a fault. So sometimes, so now you see, this is close to Renuka Lake. It is close to Renuka Lake. So if you see this is the top of the mountain, you know, you will think that this is a fault because you have lot of these sag ponds in top of the mountain. You are forming a valley, but I was thinking this is a fault and I will work on it. But later on, I came to know that it's not a fault. You know, so this is again a geomorphic anomaly. You see this, this is a top of a mountain. Something like this is okay, but top of a mountain, you have some kind of valleys formed like this. So my understanding in my mind was maybe some fault is going, and that's why you are forming these kind of valleys, which is forming a linear chain. But that is not true. This is a Sukanjan. This is known as Sukanjan, which is a slowly sinking zone. These are slowly sinking zones. So that signifies that there can be a slow movement of the slope, and someday these you might have some kind of a landslide here. So these are the geomorphic signatures of slow creeping slopes. It may not be a fault. You see this, okay. You can see that this is a forming a linear chain, like this. But these are not fault. These are not due to fault. So in Himalayas, we have, we have lot of these river terraces, and then you have these alluvial fans. These alluvial fans are formed along the river, you know, and those alluvial fans can be of both, fluvio-glacial material. It can be a fluvio-glacial material because glaciers have also contributed, and then you have fluvial influence also. Any questions? Yes, mythology also plays a role. As I showed in the first example, in case of Manikaran, that is a good example. I will say mythology plays a role, but joints, how you have these joints are oriented, that also plays very good role. Because if you see that leaf kind of a structure which is formed in Manikaran, it is definitely controlled by the joint orientation. So you need to little bit train your eye, I will say, to distinguish these factors. So now, uh, if you just see right here, you see a lot of vegetation is here, you know, just by looking at the texture, we can say that this is Shivaliks and this is not Shivalik because you have more trees, more greenery on top of Shivalik rocks. But behind that, you can see that, no, it's not. Those are Precambrian rocks, and there is a fault. MBT is passing through this area. Slowly and slowly, as you get, experience, you try to understand. Oh, okay, just by looking, and then you can also go in the field and check. Now here also, this fault is again, I will say, deflecting. Now you can see that, you know, this drainage basin is not able to go into back because this rock is different than this. So it is a kind of a barrier here. Otherwise, this basin has must have been this, and its boundary will be like here. Attachment will be here. So because this rock is hard and the fault is passing, so because of that, it is not able to grow into the back of the attachment. Because lithology is totally different. One is Shivalik, another is Precambrian rocks. Maybe limestone and like that rolls. So yes, both these factors play a definitely strong role in controlling. And then there is tectonics is also going on, active tectonic in this area. So you can see the fault is passing through Nahan, you know, and we have geology department of Nahan on top of fault. You can see right here, right? And now if you see these basins, we see that there is some these linear chains are going right. Lot of these. This is not fault. Don't confuse it fault with fault. Everything which is linear is a no. It can be bedding. You can have dipping beds. And because of lithology contrast, those are showing as a linear, trace. But it's maybe it's not a fault. But on the other hand, if it is a fault which is passing through this bedding, then it's a problem for us because we are assuming it's just bedding. Then we need to look for some geomorphic markers. Because in the books it's very easy to define a fault or a fold, but in the field when we go, then it's tough to find a fault. especially in Himalayas. I mean, now one more thing, see this drainage now. This drainage basin came, and here it has not gone. See, this river is coming here, but the drainage basin might have shifted because of tectonics. Otherwise, this would have continued like this. Here it is very, very narrow V-shaped valley of the river. But as it crosses, it flows. You can see as it crosses this zone, as it crosses this zone, it becomes, it starts meandering. So these are all these things, I think, can be worked out and can be seen that how these bases are working, how the lithology is playing control, how the tectonics is working in this area. And on top of that, you have a driving force. The driving force here is water, right? Tectonic is trying to build up these mountains. Water is trying to cut it down. And whenever there is active fault or tectonics, that is deflection, some kind of a deflection. And then we try to understand through geomorphic markers where is the fault, what is the anomaly, things like that. So in Himalaya, yes, there are lot of work which can be done. There are lot of anomalies which are present. You know, and you guys are lucky because you are just in the in the foothills of Himalayas. You don't have to travel much. Okay. So now the idea, we have understand that a drainage basin can be very older. It can have effects of lithology. It can have effects from, it might have seen lot of cycles as we discussed in the morning. Now we need some kind of a numbers, how this water is flowing this through this drainage basin, and some numbers which can tell this is normal, this is tectonic, and this is something in between. You know, so the water is flowing. We need some kind of a mathematical numbers. Now for that, what we can do is all of us know that what is vector and raster data. So in raster data, we can have digital elevation model. Digital elevation model, you have X, Y, and Z, right? And in X, Y, Z, we have softwares like ArcGIS, QGIS. In that, you can make a drainage system, to the dam. And we can develop some, or we can use some tools to identify if these numbers make sense or not. So that is what we are going to do. So if you have a computer, you can install QGIS. It's freely available, and you can calculate these. So now what we are doing is, now the exercise is what we are going to do. Basically quantifying drainage network structure. So the objective is stream order provides an objective method for describing the topological structures of a drainage basin. It reflects how streams are arranged from small waterhead channels to the main trunk, thereby defining the network's hierarchy. This quantitative approach allows researchers to compare drainage basins across different regions and geological settings systematically. Till now, what we were doing, I was just showing you, right? That this is looks anomalous. Now we are trying to put some numbers. So foundation for analysis, stream order is critical for calculating fundamental morphometric parameters. So we are going to do bifurcation ratio, stream length ratio, drainage density, stream frequency. Without stream order, basin morphometry cannot be quantitatively assessed. Geological and structural controls, structural disturbances, faults, joints, fractures, influence stream pattern and branching. right? These are you can say structural fault. If it is an active fault, it can come into tectonics also. So joints, you know what is a joint, right? So joints are basically parallel sets of these, planes. You know, generally in Himalayan rocks, for example, in lower Shivaliks, we find 2 to 3 or sometimes 4 to 5 sets of joints, right? There is a difference between bedding plane and a joint. It is very important in the field when you take dip and strike data that first of all you should first find what is the bedding plane. Where is the bedding plane? Sometimes we can confuse a joint as a bedding plane. So you need to take care of that. So tectonic uplift, active uplift creates distinctive drainage patterns and irregular branching. If there is some kind of a upliftment, so that will create a different type of a drainage pattern. Lithological variations, different rock types control stream development and network complexity. So the best example, as I just showed you, lithological variation was Manikaran. In Manikaran you saw that leaf kind of a drainage pattern. So that is definitely lithologically controlled, right? If that leaf is broken in between, then I will say there is a fault. So that is a good example which you can see that you have lithological and then drainage rearrangement, stream piracy, network reorganization reflect geological evolution. High stream order accompanied by irregular branching pattern often indicates structurally controlled drainage networks common in tectonically active regions like in the Himalayas. Hydrological characteristics by stream order. Higher order streams drain large areas, carries greater discharge, have gentler slopes, exhibit higher stability, lower erosive power compared to headwater streams. Lower order streams more numerous throughout the basin, steeper and more erosive, dominant contribution to sediment supply, sensitive to land use changes, and responsive to rainfall variation. So stream order can help to interpret the hydrological responsiveness and sediment dynamic of a basin, providing insights into how water and sediment move through the landscape. Watershed management applications, flood risk assessment, stream order helps identify critical flow pathways and areas vulnerable to flooding during extreme events. Erosional susceptibility, lower order streams control slope erosion while larger order channel transport sediment downstream. Ecolo- Ecosystem management, different stream orders support distinctive ecological communities and require tailored conservation strategies. Channel stability analysis, understanding stream order help predict channel behavior and plan infrastructure accordingly. Now, these are some of the practical steps generating stream order from the digital elevation model. So, what is a DEM? All of us know that DEM is a digital elevation model, is a raster data set. So, in GIS, we have two types of data set, whether it's a vector data or a raster data. So, DEM is a raster data where each cell contains elevation values representing the terrain surface. It serves as the foundation for all hydrologic flow modeling. Quality measure requirements free of artificial sinks. Sometimes these dams have errors, they have sinks, and pits that interrupt natural flow. These are some small errors, these are small errors in the data which we need to remove before doing any processing. Okay. Appropriate resolution for your study scale, accurate vertical and horizontal datums. Essential pre-processing. Before flow analysis can begin, the dam must be conditioned to ensure continuous flow paths across the entire surface. Critical first step, all things to eliminate depressions that would artificially trap water and prevent realistic downstream flow modeling. Okay. So basically what we are doing in this, there are in raster model basically uh, there are kernels, kernels can be used for calculating slope aspect, things like that. So when you have a raster data, so let's say we have a some elevation, digital elevation model, DEM of any area. So basically these are the columns and then you have rows. So these are the different cells which are present in a raster. So we can have an algorithm which is known as kernel, in which we can take nine values, these nine values of elevation, and then we can calculate a formula to know the slope of where is the slope of this these elevations, you know, and then we can also have we also want to know, if the elevation is higher because all these cells have x, y, and z value. Z is your elevation. So when we have a raster file that has a lot of data points, so what will the computer do? It will it will take a matrix 3 by 3 and it will try to calculate at every cell what is the slope direction and in which direction then water will flow, right? So that is the basic calculation it will do. And slowly it will calculate in each cell what is the direction of the flow. And then it will know in which direction the water will flow. And before doing this, if there are some errors, like we have, some kind of a error, then what will happen if let's say this value is some kind of a sink, error sink, it's a sink. So all the water will just go inside this. Nothing will come out. So so we need to remove these errors, by doing pre-processing. What we can do, we can put some dummy values or, we can say that no value is null value so that this is not a sink. If it is a sink, then all water will just go here. Nothing will come in this side. So that is just to remove the errors from the dam. So that is the first critical step, fill sinks to eliminate depressions that would artificially trap water and prevent realistic downstream flow modeling. So first step will be fill the dam to remove sinks. Identify the problem. Raw dams often contain artificial depressions or sinks, low points that trap water flow due to data errors or processing artifacts. Then apply fill tool. Use RGS tool spatial analysis to automatically raise the elevation of sinks cells to their pour point, ensuring water can flow out. Validate output. The filled dam eliminates artificial stops in water flow paths, creating a hydrologically correct surface ready for downstream analysis. So this tool location is in spatial analysis tool, hydrogeology and fill in RGS. You can go there and you can remove all the sinks. Now calculate the water flow. The D8 method, the flow direction tool implements the D8 algorithm which evaluates the 8 neighboring cells surrounding each grid cell. Each cell is assigned a directional code indicating which of its 8 neighboring receives flow based on the steepest descent path. So we have, basically raster file is just a file which has a lot of numbers. So this software is just trying to understand in which direction the water will flow. So understanding the output, the resulting flow direction raster uses power 2 of coding. One is east, two is southeast, like that. These are different directions. This raster becomes the routing network for all subsequent hydrologic analysis. So the tool location is spatial analysis tool, hydrology, flow direction. And then this coding is done. We run this algorithm on top of this raster layer and we can get the fractional coding. Now calculate flow accumulation. Input data, flow direction raster defines the routing network. Accumulation process, a tool counts all slope cells flowing into each cells. Stream identification, high value reveals natural drainage channels. The flow combination tool creates a raster where each cell value represents the cumulative number of upstream cells contribute, contributing flow. Cells with high accumulation values indicate potential stream channels and drainage pathways. So the tool location is spatial analysis tool, hydrology, flow accumulation. And now we can see that, in each cell, the software has calculated the flow direction and it is showing in this first diagram the flow direction. And then you have flow accumulation where the flow will come, from different cells. Now we can see that there is a value of 7, 5, and 20, 24, 25. So the water is coming and it is going into that cell. And then next step is define stream network, applying the threshold concept. Not every cell will accumulate flow in stream. Threshold values separate actual stream channels from overland flow paths. So one is choose threshold value, select accumulation value based on dam resolution and landscape characteristics, commonly which ranges from 50 to 500 cells for a resolution of 30 meters. Refine and validate. Compare derived stream with aerial imagery or reference data. Adjust threshold if network is too dense or sparse for study objectives. So threshold selection is iterative. Lower values create denser networks. Higher values show only major channels. So now, basically, after doing this step, you are able to generate the stream order. One, two, like that, three and four. Okay. Now assign stream order. That is the fifth step. Using stream order tool, the stream order tool requires two input: your binary stream network raster and the flow direction raster that defines the connectivity between stream segments. Choosing your method, installer method. We have discussed the installer method before also. So first is your headward stream, no tributary flowing in, and 2 plus higher order formed by confluence of equal order streams. So a output a raster where each stream cell contains its calculated order value, revealing the hierarchical structure of your watershed. You can see that. So if we are one is mixing with one, then you have second order, and then two and two is making the three, three and three like four. Okay. So now in the final step, we convert to vector format. Start with the stream order raster. Your classified stream network currently exists as gridded raster cells with order values. Convert to polylines. Use streams to feature tool to transform raster streams into vector polyline features suitable for mapping and spatial analysis. Optional smoothing applies smooth line tool to reduce stair step appearance and create more natural looking stream lines for professional orthographic output. Because we are working in this Raster, in raster you can have these cells, coming look like a stream. That is sometimes it is not true. So that is why we need to do some kind of a smoothing so that it looks natural. So vector format enables attribute queries, network analysis, symbolizing by order, and integrating with other geographic datasets. So first is this bifurcation ratio. The bifurcation ratio expresses the relationship between the number of streams of one order and the number of streams of next higher order. The bifurcation ratio BB is the fundamental morphometric parameter used to quantify the degree of branching in a drainage network. Proposed by Houghton in 1945 and widely applied using Staller's ordering system. A bifurcation ratio provides insights into the structural, lithological, and geomorphic characteristics of a watershed. Because drainage network reflects the influence of geology, climate, and topography. Bifurcation ratio serves as an important indicator of tectonic control, drainage evolution, and landscape dissection. So the formula is RB is equal to NU upon NU plus 1. Here NU is the number of streams of order U, and NU plus 1 is the number of streams of the next higher order. This calculation is based on Staller's stream ordering system, the most commonly used method in geomorphology. Now, here you are given some handouts on which you are to calculate this thing, bifurcation ratio. So, generalized classification of bifurcation ratio. So, if the bifurcation ratio is less than 3, it is classified as low. Between 3 to 5, moderate, and more than 5, it is high. So, low indicates homogeneous rock, weak structural control, youthful drainage, and a dendritic pattern. Moderate normal drainage behavior, moderate structural influence, common for most basins, and high value represents strong structural and tectonic control. Elongated basins, talus rectangular patterns, active tectonics. If you, let's say your number is RB, this bifurcation number is more than 5, let's say you have 10 or more than that, then yes, you can think of that, yes, this drainage basin is affected by active tectonics. So now we are getting some kind of a number. Previously, we were just having a visual look of different basins. Now this bifurcation ratio is helping us to identify basins which are can be active. Okay, so this is your first exercise. You need to mark the stream order and calculate the bifurcation ratio. So I think we can also start the practical now. Okay, so all of the students must have been given the practical sheet. So now you can start doing the practical. So count the number of streams in each order while calculating the bifurcation ratio. So you need to count the number of streams in each order. So you can use this formula RB is equal to NU upon NU plus 1.